Little data, I found you on my calculator. Little data, it seems like you've something to share. Here comes the stat, data data. Hello everyone and welcome to today's lesson, the beginning of Chapter 2. The data that you see before you represents over 5,000 titles taken from Netflix in 2022. We have The Power of the Dog, The Sinner, and all of these are either movies or shows. We also have their IMDb rating. And the key guiding question we have for today's lesson is what's better on Netflix, their movies or their TV shows? Today's lesson, association between two categorical variables. And today we have three skills: 2A frequency tables, segmented bar charts, and describing the associations that we see in 2A data. Now this might look a little bit familiar because you've seen one-way frequency tables before. As a quick reminder, a one-way frequency table represents the frequencies of one variable. This is from back in Chapter 1. The variable that we looked at then was leisure activity. And even though there are three entries, they're all part of the same single variable. Leisure activity can be music, TV, or reading. And in Chapter 1, we represented that in two ways. With a bar chart where we put each value of the variable in separate bars, or with a segmented bar chart, where we put the values of the variables one on top of the other. When we look at two-way categorical data, we're adding in a second variable. So we still have our previous variable, which was leisure activity. It had three types. And we're now adding an extra variable, which is the age of the people who are taking part in these activities. In this case, teenagers or adults. When we represent these in a chart form, we're not going to do plain old bar charts anymore, because that would be like 6 different bars? Are they going to be behind each other, in front of each other? I don't know. Instead, we make a segmented bar chart for each value of one of the variables. So our teenagers from the age is one segmented bar, and the adult's value of the age variable is another segmented bar. So why are we doing this? We're doing this because we want to understand something about the data. We want to see if the data is telling us something. A question that I could ask of this data is, who likes music more? Is it teenagers or is it adults? What do you think looking at this table? Now you might say, well, I can see we've got 6 teenagers for music, 3 adults for music, teenagers like music more. And you would be correct. But the reason why you're correct is because the total for each of these columns is the same. If the total is different, then our analysis is going to have to be a little bit different. Even though in this table, the same number of teenagers and adults like music, it might not represent the percentage of the entire group. So that's why we're going to find the percentage of two-way frequency tables. Let's find out the total here, 6, 10, 4, and the total here, 6, 10, 24, 30, 40. So if I really want to analyze this question of who likes music more, I'm going to have to put up percentages. Now back in Chapter 1, we looked at how to find the percentage frequency. It was with this formula over here, and I'll do an example for you. Let's say I wanted the percentage frequency of teenagers who like music. I would take my 6, I divide it by 20, I times it by 100, and 6 out of 20 is the same as 3 out of 10. It's going to be 30%. For the second one, teenagers who like TV, that's 10 out of 20. We know that's straight away 50%. And for teenagers who like reading, 4 out of 20. 4 out of 20 is 1 over 5. That's 20%. Now, if you want to see how this is done on the calculator, because you're not as comfortable with working out these percentages in your head, then let's do a little quick example. So for the percentage of adults who like music, well, we've got 6 adults out of a total of 40 times by 100. Who knows what it is? 15%. Full table over here, and this is the table of the percentages. 30%, 15%, etc. Now, once we have these percentages, we can start to understand more how to answer the question of who likes music more. Well, 30% of teenagers like music, and only 15% of adults like music, so it seems like, according to this very formal and official data, that teenagers like music more. And we have all these ideas for you summarized on this slide here. Do you think you're ready for a question? So to help us answer this question of what's more popular, we're going to want to turn our raw data from our 2A frequency table into percentage frequencies, and then turn it into a segmented bar chart, because that visual image might help us understand what's going on. First step, add the totals. Then convert to percentages. So just as an example, this 11 came from 367 out of 390 times 100. These are all percents. And once we have these as percentages, we can turn them into a segmented bar chart. So here we have a wonderful segmented bar chart representing the percentage frequencies from our two-way percentage frequency table. The movies between 2.5 and 5 was 12% of all the movies. And I can see here that that value there is 12%. Then the next group in our movies is 77%. So I go 12 plus 77. What does that take you to? 89. I can see the total height of this bar is 77. And then there's a nice little 11 added on the end. So your lowest bar will be nice and easy to see. It matches up directly to a percentage. But the other bars, you have to do this bit of addition to work out where they're going to finish. What are some other nice features of this segmented bar chart? We have the bars not touching. We touch when we have histograms, but bar charts are separate. And we've put in a title and a legend to explain what our different colors mean or different sections mean. If you don't have colors, then you can also shade in using different patterns. So some people might go like that for one of the sections, and then you could do a dotted section for another, and you could leave it blank for another one. And then you would make your legend using those. One thing to note, just keep an eye on this, is that we totaled vertically going up and down. All these together add to 100%, and all these together add to 100%. And there are two of those columns, and there's two bars. One cause of confusion is that often students don't know which way to total the data. What if we were to total this way? We add up these numbers, and these numbers, and these numbers, and these are our totals. And then all of those, like 407, is a total out of 487. What would happen there? And why should we do one and not the other? Well, if we were to do it that way, we would be making 100% out of our IMDb score categories. And if we had 300%, we would have 3 different bars. So the way that you choose to add up your totals will define how your segmented bar chart will look. But warning, generally we don't add up going horizontally. Unless otherwise specified, always add up vertically. And the reasoning behind that is we want to add up the total along the explanatory variable. So here, if I think about my research, I'm trying to say, well, I think the movies get a certain score and the TV shows get a certain score. It's not the score that causes the thing to be a TV or a movie. It's the fact that it's a movie that causes it to be a high score or a low score. So I don't want my IMDb score to be on this horizontal axis here. That's a general rule. It's not a hard and fast one, but it's a general rule for when we're looking at two-way segmented bar charts. The best way to do it is like this, where we add up vertically and we put our explanatory variable on the x-axis, because we're asking how are these IMDb percentages changing as we switch from movies to shows. And this shows that to us visually. Cool. Does that make sense? I've got those ideas summarized on this slide over here, and we're going to use them now to tackle the question. Once we have our wonderful segmented bar charts, we're often asked to do an analysis to answer the question of, is there an association between the data? And when we give an answer to that kind of question, we're going to want to do 3 things. First of all, answer directly. Is there an association or is there not? When we do that, we need to support our answer by comparing relevant percentages. And we'll usually also put in the names of the variables being analyzed. Is that making sense? How about we see an example to see how it's done? So have a look at this segmented bar chart and tell me, do you think there's an association between the type of title and its IMDb score? Yeah, I can see that as we go from movies to shows, the amount of bad ratings drops and the amount of good ratings between 7.5 and 10 increases. So from these 5,000 titles across Netflix, it seems to be that Netflix's TV shows might be more popular than their movies as a whole. How are we going to answer that in terms of giving a report on the data? Well, we're not going to want to quote every single percentage here. We can pick a specific value of one of the variables and talk about that one. So how about we talk about the number or the percentage of titles that are in the highest rating? We would do it in a way like this. Is there an association? Yes, we say there is an association between Netflix type and IMDb rating. Notice there that we're naming the variables that we're looking at. We now want to quote some percentages to support our answer. We say that 11% of the movies have a rating between 7.5 and 10, and 33% of the shows have a rating between 7.5 and 10. And that, quoting of that difference in percentage, is enough to show that there is an association between the two variables. All right, and those are all the key ideas from today's lesson. I'll see you next time for the association between numerical and categorical variables. Little data, I found you on my calculator. Little data, it seems like you've something to share. Here comes the stat, and I say it's alright. Hi everyone, and welcome to today's lesson on the association between numerical and categorical variables. We're going to be exploring some data sets we've seen before, the AFL and Titanic, but we're going to be adding more data. In Chapter 2, we're moving into bivariate data. We're looking at two different types of data. Last lesson was categorical and categorical, and we're moving our way towards the really cool analysis we do with numerical and numerical. Here, we're getting that middle ground, mixing categorical and numerical together, and seeing if we can interpret what's going on there. We're going to not just describe the data, we're going to begin to interpret it and analyze it to draw conclusions. There are two main skills we're going to be looking at in today's lesson. The first one is numerical and categorical variables, and understanding how they look in different data displays. Which data displays can we use for these? Is it histograms? Is it box plots? Is it a scatter plot? And then once we understand what those displays look like and how to interpret them, we're going to describe the association that happens when we put two side by side. Putting them parallel is what's going to allow us to compare and understand associations. Well, what does that look like in practice? Here's an example of parallel box plots. And by showing Richmond's tackles per round in 2 different years, we can start to ask questions of the data. We can say, was Richmond a better tackling team in 2017 than it was in 2015? Now, the mighty Richmond Tigers won a premiership in 2017. And in 2015, I think they finished 5th and were knocked out in the elimination final. We can clearly see, we know there's an improvement, and we can actually see this in the data itself. I'm personally not a Richmond supporter, but my good friend Peter is. And Peter, if you're watching, hello. But why is this specifically a display of numerical and categorical variables? Well, we can see that our tackles are clearly numbers. It's a numerical variable that ranges from 30 to 95. And the years becomes a bit interesting because a lot of people think that in this scenario, the year is a numerical variable. But actually, year is a categorical variable in this situation. It's like 2 different time periods, then and then. And those are 2 categories that we're analyzing and trying to compare between. Were they better then or were they better then? We're not really looking at the order of the years. We're not trying to measure the years. We're saying Tigers 2015, Tigers 2017. Who's better? And that's why a parallel box plot and this specific example works for a numerical and a categorical variable. We'll come back and analyze this a little bit later. Another display for analyzing the association between categorical and numerical variables is a back-to-back stem plot. Here we have our stem plot that we recognize. This is our stem. And then we have our leaves on the other side. And we sort of split off to the side like a double-sided tree. And each side represents a different value of the categorical variable. What do I mean? Here we have a numerical variable as age. And we're trying to compare the ages between 2 categories. The first category is the women from England who were in the 3rd class section of the Titanic. And the second category is the women from England from Britain who were in the 1st class of the Titanic. Isn't that lovely, Governor? So all of these 3 things, back-to-back stem plots, parallel dots plots, and parallel box plots can be used for this kind of purpose. I've got a question for you now on the parallel dot plot. See if you can work out what's going on there. All right, now we understand these different displays, we understand how they can be used for numeric and categorical variables. Can we start to interpret what's going on and draw some conclusions from the data that we see? I've added an extra year of Richmond's tackles here, 2016. What do you think about these box plots? Do they show a change in Richmond's tackling over our 3 categories of years, 15, 16 and 17? Now you might have an answer to that question. I think you do. But when you come to express that analysis to someone else, there's a few things you want to make sure you tick off to really back up the thoughts that you have or the understanding that you have from these box plots that you see. We want to do three things. Number one, we want to quote the values of an appropriate statistic. So either we can quote something for center, for shape, or for spread. And if you remember right, for center, we could use median, shape is our skew, and spread is interquartile range or range. There's a range of options for these. Then we don't want to just quote the values. We want to actually explicitly say whether or not there is a significant change. Is there an increase? Is there a decrease? And lastly, we actually need to summarize our contention about whether or not this does support an association. Let's see how this looks in our example with our box plots. So it looks pretty clear that Richmond's tackling is improving over the years. But I need something concrete to explain it with. So let me look at the statistics. Let's say I want to quote the median, which is what we're going to do. I could take the median from the actual box plots themselves, but I would just be giving a rough answer. And if that's all you have, it's totally fine to use that. But if you were doing some analysis previously and you actually have the numbers, then better to use the numbers themselves. So I pull up here our numbers. That's another word for Q1. That's another word for the median or Q2. That's our Q3. And if I'm going to use the median, I'm going to talk about these three values here. So let's bring it all together and look at our sample answer. Remember, we're looking for three things: quoting the statistic, saying whether there's a change, and actually giving our contention whether we have an association or not. So yes, we think that there is an association between tackles and year. Looks pretty clear from the box plots. How do we support it? This is seen by an increase in median tackles as year increases. So this is the part where we're describing the actual change that we're seeing. We're not just quoting the numbers. We're saying, oh, it's gone up, it's gone down, or there's been a change. Now we go and we quote the statistic that supports our answer. And we're quoting the median. Richmond's median in 2015 was 56.5. In 2016, it was 59. And in 2017, the median was 68.5. And that's a really good way of supporting our contention that Richmond has basically improved, that there is an association, because the median shows the center of the data. And if the center of the data is moving, that's an indication of what Richmond is doing generally. Just one little point. When we talk about association, we're not talking about causation. We're not saying 2017 caused Richmond to do better. Like, there are other things going on. Richmond had planning meetings and they changed the strategy, or they put more emphasis on this. There's an association between the variables. It seems to be that as one changes, the other one changes, but an association doesn't mean causation. We're going to talk about that in a later lesson. All right, most of the time, you're going to just use median. It's a really great tool. It's a great statistic. It's often easy to find, and it supports these contentions about association really well. But just to give you an example of another one you could use, let's try and write our analysis using the statistic of spread and specifically interquartile range. So when I talk about spread, I could use range or I could use interquartile range, but I prefer to use interquartile range because range includes outliers. And just my personal opinion, I think interquartile range is often a true description of spread. Anyway, you take your pick. Let us do some analysis. To get interquartile range, we're going to need to do median. I'll do this a little bit quickly because you've seen it in a previous lesson. Our top chart has 19 points. 19 plus 1 over 2, 20, 10. So the 10th point, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's our median. Then there's 9 on either side of the median. So 9 plus 1 over 2. That's the 5th point. 1, 2, 3, 4, 5. So Q1 is there. And then I'm going to go 5 here. 1, 2, 3, 4, 5. And that's Q3. So interquartile range is 9 minus 6, which is 3. The bottom one has 24 points. So 24 plus 1 over 2, 25, 12 and a half. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 and a half. Halfway in between is this point here. It's going to be 4. That's our median. Then there's 12 on either side. 12 plus 1 over 2, 13, 6 and a half. So between the 6th and the 7th point, 1, 2, 3, 4, 5, 6, 7. So it's there. That's our Q1. And then 12 points here. 1, 2, 3, 4, 5, 6 to the 7th point. That is our Q3. So interquartile range, 8 minus 1 is 7. Great. So those are statistics. Interquartile range of 3, interquartile range of 7. How can we put it into an answer? Well, let's just sort of step back and understand what we're doing here. We're saying, is there a difference between Felix and Fergus? And yeah, it looks to me like Fergus has a lot of really quick calls, but a few longer calls. Felix's best isn't as good as Fergus's best, but is more consistent. So the fact that Fergus's data has like spreads more is significant. It's important. Like if you were the boss of these two people and you're like, who do I prefer as a worker? Well, maybe you'd prefer Fergus because you get a lot of really happy customers, but you also get a lot of sad customers as well. So how spread this data is actually really like an important factor in your analysis. But we're just asking, is there an association? Is there like a difference between Felix and Fergus? And yet the fact that they have different spreads does show that they are different kinds of operators. How do we answer it? Yes, there is an association. Tick. We need to describe the change. This is seen by a change in the IQR of the waiting times between Felix and Fergus. So that word change is important. The word change, the word increase, the word decrease, either one of those three is fine. And now we quote the values. Felix's interquartile range was 3 minutes and Fergus's interquartile range was 7 minutes. Tick, tick, tick. All right, here are the key ideas from today's lesson. I'll see you next time for the association between two numerical variables. Here comes the stat, and I say it's all right. Hi everyone, and welcome to today's lesson. I'm really excited to introduce you to two new data sets. The first data set comes from the Gallup World Survey of over 150 countries. It tries to explore the question, what makes people happy? And two of the variables of data we have there are the GDP of the country and the life expectancy of people in the country. We're going to look at the association and the connection between those two variables. And if there's anything more important to us than our life expectancy, it's whether or not we have an internet connection. Our second data set looks at the price of mobile data across countries around the world. And of course, we have finally arrived to looking at the association between two numerical variables. I'm excited. We're going to do lots of modeling on this kind of data. Today's a bit of an introduction to these ideas. We're going to be doing our analysis and our modeling and our predictions a bit later, but we need to get our fundamentals right. Tackling, pressure, marking, ground balls. Explanatory and response variables, interpreting a scatter plot, and then looking at the direction, form, and strength and outliers of our scatter plots. Explanatory and response variables are two variables. And you'll notice that from chapter 1 to chapter 2, we have made the jump from one variable to two variable. The words we use to describe this and define this are univariate data and bivariate data. How do you remember the difference between the two? Think of a unicycle and a bicycle. Bicycle meaning two wheels. That's me riding around on my bicycle. So I was thinking that we get a unicycle and some juggling balls and circus music and I ride around the studio. Yeah? A later lesson? Okay, cool. One of the tasks we like to do when we're given two sets of numerical data is to identify which one is the explanatory variable and which one is the response variable. That's really important if you're building a machine learning model where you have your features and you're trying to predict your target. We practice that over here. The explanatory variable is always on the x-axis, horizontal. Notice the letter X in the word explanatory. And the response variable is vertical, it's on our y-axis. Why are they called explanatory and response? Vika deliberately chose those names to describe what they're doing. The explanatory variable is the one that explains what's happening in the response variable. We say, if we change something in the explanatory, we're expecting something to change in the response. Now, we're not going to jump ahead and say that the X causes the Y. We're going to talk about correlation and causation later. To prove causation, we're going to need to really have some strong scientific experiments. But if we hypothesize, if we think that one would have an impact on the other, we put that one down the bottom on the x-axis. We can also identify which one is the explanatory or response if we're given a linear equation. The explanatory variable is the x in the equation on the right-hand side, and the response variable is the y. Sometimes we also identify these two variables from tables. Now, it's not a hard and fast rule, and sometimes Vika will swap it just to trick you. But very, very often, the explanatory variable is on the left, and the response variable is on the right. And so too, if it's a top-down table, the explanatory will be on the top, and the response will be on the bottom. Now, I'm not saying it's a hard and fast rule. You always got to actually think about the variables and say to yourself, does one explain the other? Which one is which? But you'll probably see that in like 90% of the tables that you have, this is the scenario. Researchers had a theory that the bigger a country's population, the cheaper its internet prices. So we're saying the countries with a bigger population have cheaper internet. Maybe, we'd have to do some data to check that. But if that's our hypothesis, which of these is the explanatory and which is the response? Well, we're saying a change in population causes a change in the internet price. So the population is what is explaining the response. Population goes down here, internet price goes here. And if we were writing an equation, we would put the words internet price on the left instead of the y, and our explanatory variable, population, on the right instead of the x. So I spoke about those two data sets, and they weren't just hypothetical questions. They were questions that I've actually made an attempt to analyze. I've taken the data of population and internet prices. And if you look over here, we can see that we have lots and lots of countries. I've cut out a few of the outliers because when we do machine learning and when we do analysis, we generally don't want to have outliers in there. We want to look at the trends that happen with most of the data. So, for example, China and India, you won't see here, their population sizes are like 1 billion. We can see that we have Australia. It has a population size of about 25 million. These days, it's gone up since this data was taken. And the average price of 1 gigabyte in Australia was 70 cents. 70 cents in US dollars. Have a think about your data plan and see whether you're above average or whether you're below average. But what we can see here with a scatter plot is that every single dot is representing a country. Up here, Cyprus, low population, very expensive internet, not doing so well. Who's doing pretty good? Who's this guy? Italy, pretty cheap internet there. So this is a scatter plot, and we're now going to take this data and analyze it a little bit more, and maybe in the future we'll start to do some predictions and some modeling. Now, in general maths, we generally don't do analysis on millions of pieces of data. We take a small data set, something that we can handle on our calculators, something that we can understand, and we try and understand what's happening over there. You might have seen on the bigger graph that there seemed to be an association. I've taken a sample of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 data points, and that represent a little bit of what's going on in the bigger picture. Let's analyze this and see what's going on. Which of these is the explanatory variable? It's on the x-axis. It's population. How many numerical variables are there? It's not how many data points. It's the variables, population, and the average price of 1 gigabyte. 2. How many countries were investigated? Remember, each of these is a country. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Verification. And part D, what was the average price of 1 gigabyte for the country with the highest population in the data set? This little country over here, highest population is actually Vietnam. And they're doing pretty well with internet prices. Each of them is about 0.5. I haven't told you, but the information will be there in the context of the question. I'll let you know now that the y-axis is actually in dollars, so it'll be $0.5. And because we're doing finance and financial maths, we're going to also put in the 0 there to show that it's 50 cents. Just FYI, that's US dollars. All right, we now have our second data set, which was from the Gallup World Survey that tries to explore the happiness of different countries. 2 of the variables in that data set are the GDP per capita and the healthy life expectancy. Now, life expectancy is how long do you expect people to live in your country. Healthy life is how long do you expect people to have a healthy life. So people might live long, but if the last few years of their life aren't so healthy, then maybe that's not as valuable. Philosophical questions. So this specific data is how long do they have a healthy life. I'm going to give you a multiple choice question on this now, see if you can understand what's going on. Alrighty, we're going through our terminology, all of this like setting the ground, setting the playing field for all of the analysis we're going to do in the coming lessons. We talk about direction. Direction, are you going up, are you going down? We always walk from left to right. If you're going uphill, it's positive. If you're going downhill, it's negative. And if you ain't got no direction, no association. We can talk about form. The data that I've showed you so far had a non-linear form. It was like curving up or it was curving down. And we're going to be learning different tools for analysis. Some of those tools will only work on linear data. Then another tool we can use to transform linear data to get to work on other stuff. Anyway, you'll see. Now we talk about strength. So how strong is this relationship? We have our data, and if there's a lot of strength, then we can see that one variable really is very strongly correlated with the other one. We might be able to use that to predict the other one. If it's not so strong, if the data is weaker, then when I build my machine learning model to predict the happiness of people or the life expectancy of people in the country, I would predict that my model is going to make lots of errors. And depending on the environment you're working in, you might be happy with those errors or not. If you're in the medical industry and you're creating drugs and cures and treatments, you want to be pretty sure that you're doing the right thing. If you're in finance and you're making investments, and you don't mind if you lose $2 million here as long as you make $10 million there, you can probably be okay with some weaker data. Anyway, that's some of the reasoning behind why we might look at these kinds of things. Data is stronger when it's closer together. So don't worry about the R for now. We'll talk about that in a later lesson. But tight is strong, less tight, moderate, not so tight, but still with direction, we call weak. If it's a perfect association, which we never see in real life unless there's some problem in your data, that's like a one-to-one relationship. And if there is no association, then our data is just scattered everywhere. Like my brain. Here we have that data with the population and the internet prices. If you remember, what I showed you had cut out India and China, which are two outliers over here, because I wanted to see what trend was happening inside the main data. When I build a machine learning model, I want it to really fit through the main data points, the few hundred data points that represent most of my data. So when we do analysis, we like to cut away our outliers. You're never going to see a question like this in VCA because there's 200 countries and that's a lot of data points. These ones are definitely outliers. These ones, just because there's so much data over here, these are also probably outliers as well. What am I trying to say? I'm saying that VCA will be clear. You'll have a clear understanding. And you'll only usually have 20 data points. And you'll be able to clearly see which ones are outliers, which ones. This is the data after we've cut the outliers away. And now we can start to talk about trends. We can start to fit models to predict the data. All right, here's a summary slide for the ideas that we've looked at. I have this table here that describes based on the R value, whether you are weak, moderate, strong, no association. We're going to dive more into that next lesson when we look at Pearson's correlation coefficient. All right, we've laid the foundation. We understand the key features of our scatter plots for numerical data. We're going to start to look at correlation and causation. We're getting into the realm of making predictions. Here comes the stat, and I say, it's all right. Hi everyone, and welcome to today's lesson. Who is this guy? Is he your long-lost uncle? This is Carl Pearson, who gave you Pearson's correlation coefficient. That's a bit scary. We might call him Fearsome Pearson. But actually, this guy is an absolute legend. There are some mathematicians in history that you look at what they did in their lives and they came up with so much and you think, how is that even possible? So just to give you an idea, a lot of the things that you've come across, Pearson came up with them. The word histogram and the idea of a histogram, someone had to invent these things. A histogram is so useful. I use it in the machine learning work all the time to just print the data and see what I'm looking at before we build any models. The word mode, he came up with that. Mode. Why would you call it a mode? Anyway, what else? Principal component analysis, that's used in machine learning when you have features up to, hundreds of dimensions big. The chi-squared test, that's used when we do non-normal distributions. You know how everyone's teachers everything is normally distributed. And you're well, is it all normally distributed? Well, it's not. And chi-squared is one of the things used in research when it's not. Contingency tables, those are these kind of probability tables you might have looked at in Year 10 maths. Random walk. Random walk is the basis for Brownian motion, which formed the basic theory of the Black-Scholes model, which Black and Scholes earned a Nobel Prize for in 1968. That forms the theory for option pricing in the share market. And so it basically forms the foundation of a lot of the finance we have in our world today. So Fearsome Pearson, more like King Carl. His first name's Carl. One of the things he gave us is the Pearson's correlation coefficient, and we're going to be looking into that today. Part 2, which you'll see next lesson, is looking at the idea of correlation versus causation. So if you want that, jump to that there. For now, we're going to understand this R value. Where does it come from? What does it mean? When can we use it? And we'll see how we go. 4 key skills today. when can we use Pearson's correlation coefficient? How do we calculate his coefficient? Can we estimate it, get a bit of a feel of what it might be from the data? And because it's very connected to this other concept called the coefficient of determination, I'm going to show you how you calculate one from the other. Last lesson, we looked at the strength of the association between two numerical variables. And we said when the data is close, it's strong. When it's further apart, it gets weaker. And you've probably seen that these numbers, these R numbers, can kind of be used to describe the strength. So that R is Pearson's correlation coefficient. But before we start to analyze it and calculate it, we have to understand when we're able to use it. Hold your horses. Nay! We can only use Pearson's correlation coefficient if 1. The association is linear, 2. There are no outliers, and 3. The data is numeric. And just to prove why this is the case, I created some data and I calculated Pearson's correlation coefficient for it. But this data that I created does not fulfill the criteria. So this is non-linear data. And you can see it's actually really strong. If you were to build a model to predict what's going on here, your model would be really, really good. You could give it an explanatory variable and the response variable it predicts would be a really accurate one if you used a non-linear model. But if you try and calculate Pearson's correlation coefficient, you're just going to get 0.3. And this data doesn't look like a strength of 0.3. That looks like really strongly associated data. So what am I trying to say? We can't use Pearson's correlation coefficient for nonlinear data because the correlation coefficient assumes the data is linear. It's trying to fit a line like this. And yeah, those data points are really far away from the line. So that's why we get a really small R value. We also can't use it if there's outliers, right? We can see that this data is really strong. Yeah, and it's got strong association. But because I've put an outlier here, when we run a linear model through it, it's going to put the line, I don't know, somewhere like that, or somewhere like that, or somewhere like that. It's not going to fit it properly because it's trying to be pulled towards the outlier. And therefore, we can't use Pearson's correlation coefficient when we have outliers. Also, your data needs to be numeric. We can't fit cats and dogs and categories. We're fitting here to numeric data. All right, I'm now going to show you how to calculate Pearson's correlation coefficient. There is a formula, which is not part of the course, and you don't need to know, but just out of curiosity, you can see that the standard deviation is in the formula. And if you remember, standard deviation kind of tells you how much the data moves from the mean. So is it spread or is it close? And that's a bit of an intuition as to why that might be connected to the correlation, like how strongly correlated is our data. Anyway, you can basically ignore that formula. I'm going to show you how to do it on the CAS. All right, I'm going to show us how to calculate Pearson's correlation coefficient on the TI Inspire calculator, but I'll narrate a little bit about the ClassPad as well if you're curious to know that. As a general rule, we have down the bottom of the course lessons on how to use the calculator for both TI and ClassPad, so that's always a really good resource to go to see this in detail. But we want to put in our data. So we're going to go to Control and Doc, and we're going to go Add Lists and Spreadsheet. On the ClassPad, you can go to Spreadsheet, or you can go to Stats. Anyway, once you're there, you want to put your data in. All right, we've filled in the data. I can see that I reached row 10, so there's 10 data points. I need to also add in a name for the column. Now, in the ClassPad, you can basically just use the existing names, which is the list 1 and list 2. I'll call it something that I recognize. I'll just remind myself that X was the population. Okay, I've now got two options to find the correlation coefficient here. Control Doc, add a calculator if we didn't have one previously. And what we want to do is type in the words core mat. Core for correlation, double R, and mat for a matrix. And we want to put the names of the variables in. Now, you might remember them, but if you don't, use this wonderful button here called var, and you go pop for population, and our response variable was the Y. When you're finding the correlation coefficient, it actually doesn't matter about the order. We press Enter, and we have here, in the top right or the bottom left of the matrix, it'll always be symmetric, the correlation coefficient. It is negative 0.38. If you're on the ClassPad, you want to go calc regression, linear regression in your spreadsheet that you're in, and it will give that to you as well. And on the TI Inspire, there's actually another way to do it inside the spreadsheet, which I've written on the previous slide if you want to find that. It prints a whole range of different statistics, which could be useful for you too. All right, I want you to have an intuition for Pearson's correlation coefficient so that when you calculate it, you can ask yourself, is this reasonable or not? I have here a bunch of scatter plots, and I want you to think and guess what you think the correlation coefficient might be. We're going to start with this one over here. How strong is she? Is she positive? Is she negative? What do you think the R value would be? And you can use this summary table to decide. If it's strong, it's going to be between 0.75 and 1. All right, first one. You ready? It was 0.9. It's actually pretty strong data. What do you think about this second one up here? Negative 0.1. Oh, it's a bit of a downwards trend. It's really super weak. We actually, you know what? It's more than weak. It's no association. Between 0 and 0.25, we actually say no association. There'll always be some value to it because there's like some random connection. But anything below 0.25, we basically say no association. Next one. Yeah, negative and 1. What about the one after? Positive 0.6. Oh, next one's a bit weaker. 0.4. We're now on the edge of describing something as moderate or weak. What was this? This is weak, and this is moderate. Obviously, it's very hard to judge. You don't have to be an expert, but hopefully you're getting a little bit of a feel. Negative 0.7. All right. We've basically covered everything we need for Pearson's correlation coefficient. But there's a concept you're going to come across in the next chapter, in chapter 3, called the coefficient of determination. And because they're so closely connected, here I'm going to show you how to calculate one from the other. Pearson's correlation coefficient is R, and the coefficient of determination is R squared. So it's pretty basic. The way you go from Pearson's to the determination is that you square, and the way that you go backwards, if you have the coefficient of determination to Pearson's, you square root. But as I've pointed out in our little summary table down here, when you square root, you might need to take the negative value if you had a negative association. Am I making any sense? Let's see in the worked example how it plays out in practice. All right, when we were looking at Western Europe, we found that the connection between population and the price of internet data had a correlation coefficient of negative 0.377. That is R. To find the coefficient of determination, we square negative 0.377 squared. Now that is going to be an error because what did the calculator do? It first squared 0.377 and then it took the negative. But if you times two negative numbers together, you're going to get a positive. So how do we do this right? Let's open up a bracket. Negative 0.377, and that entire number, including the negative, is what's being squared. Boom cha. Our answer is 0.142. Answer. Here's some summary. Have fun. See you for correlation and causation.
For too long I've been parched of thirst, and unable to quench it. Too long I've been starving to death, and haven't died. I feel nothing, not the wind in my face, nor the spray of the sea, nor the warmth of a woman's flesh. You best start believing in ghost stories, Miss Turner. You're in one. Welcome, everybody, to today's lesson on correlation and causation. You think pirates aren't relevant? Pirates and global warming are inherently linked. Yeah, we got two main skills in today's class. Correlation versus causation, and observation versus experimentation. Yar. So, Somalia. You know what Somalia has? Some of the lowest global warming in the entire world. You know what else it has? The most pirates. Is there a connection? I'm going to call in Professor Timothy to tell us more.
Yeah, hello, my name is Professor Timothy. I have come back from an expedition where I have been gathering research from around the world throughout time. I have randomly sampled. Yes, remember, random is very important in our research and science. The information around pirates
and global warming temperatures. And what we can see here is that as the number of pirates has increased, the global warming has decreased. Clearly, there is a connection. We must, to reduce the global warming, increase the number of pirates in the world. Thank you.
Hey, all you followers out there, it's Jessica. So after my last video on TikTok, I decided that I would go deeper into the science behind the stock market. And what you're going to find is going to blow your mind. So what I found is that there is totally a connection between the length of your skirt and how the stock market performs. So back in the roaring 20s, everyone's skirts were like super, super low. And then booming here, low again. Oh my God, oil prices are plummeting, inflation's going up, skirts get longer. Then an economic boom, up stock market goes, stock market sink, dresses go long, and the economy picks up, it goes shut again. Like, this is totally true. This data comes from history, and I looked at the roaring 20s. Like, my auntie, Veronica, she was like totally there then. Anyway, you gotta follow this. So, you know what you gotta do now? If you want your share portfolio to go up, just change the length of your skirts. SLT, more like SL rich. So, what can we see from our Professor Timothy and our wonderful Jessica? We see that correlation is not always causation. Both those people pointed out true correlation, right? Like, that data with the pirates and the global warming is true. Right? There's just another reason as to why they're connected. And the data with the skirts in the stock market also did happen. But the fact that there's a correlation between the two doesn't mean that one causes the other. If I want to say, like, what am I going to do? Go out tomorrow, change the length of my skirt, and expect the stock market to change? That's not going to happen. What am I going to do? Like, put more pirates onto the seas and expect global warming to go down? No, just because there was a correlation doesn't mean there's going to be a causation. If I think that that's true, I should set up a proper scientific experiment to actually see whether one causes the other. Like, why would Somalia both have low emissions and high levels of piracy? It is a developing country, and those two things are associated with that third factor. That third factor is kind of like a common cause that affects both of these other two variables and is a very frequent cause of people mixing up correlation and causation. So how do we establish causality between two factors? How can we come along and actually say, well, we think A causes B? Well, it's done through a scientific methodology, and sometimes research is done through observation, like observation of things that currently exist, or experimentation, where we deliberately set up an experiment. And what we're going to find is that experimentation is really the gold standard of how we establish causality. So let's take an example. Let's say you work for the National Bowel Cancer Screening Program, which is a wonderful organization trying to increase people's awareness around getting screened for bowel cancer. There's a test that comes in the mail over a certain age. You can do it, and doing it basically drops people's chances of getting bowel cancer. And it's really, really good. It reduces, obviously, like, saves lives. It also reduces costs of the medical system. So it's in everyone's interest to get this happening. Let's say that you wanted to increase the number of people who were going and doing this screening. So what you might do as a government, you might say, I'm going to observe. I'm going to look at people who have seen ads online for this National Bowel Cancer Screening Program, and I'm going to then ask what percentage went and got screened. And my theory is that those who saw the ads did the screening, and those who didn't see the ads didn't do the screening. So I go to Google, I get my data, I go, thanks Google, and I start to do my analysis. So let's model what happened here. We have some people who saw the ads, and we have some people who didn't see the ads. And then out of those two groups, we ask, all right, what percentage went and got screened? Well, for those who saw the ads, I'm going to make up some numbers here. 80% of people got screened. And for those who didn't see the ads, only 25% of people got screened. So we go, aha, wonderful. It looks like we should do more ads. Let's put in, I don't know, $10 million, make some great ads. What's the problem here? What's the problem? The problem is that we are making a conclusion based on observation of what happened historically, and we're not accounting for the confounding variables that could happen here. Do we think that these two populations, the people who saw the ads, the people who didn't see the ads, are like equally representative of the same kinds of people? The answer is no. we know that Google likes to show you ads for things you've looked at in the past. So someone who's gone online and checked up symptoms for bowel cancer is more likely then to have been shown ads. So they're more aware. And there's a whole range of different factors that would cause this group of people to be different to this group of people. And then it might just be that this 80% came from the other factors and not from the fact that they saw the ads. These people are more aware and more vigilant about their health, and maybe that's what caused them to go and do it. How do we actually establish causality? Well, we want to set up a nice scientific experiment. We're going to randomly sample from the population, and we're going to put people into two groups. We'll put an experimental group up the top, the ones that we show ads to. And down here, we'll put our control group, the ones that we don't show ads to. Then we randomly sample from the population, and we put in both groups an equal representation of all of the factors that we're trying to control for. So in the experimental group and the control group, there'll be people who see ads who browse online. There'll be people who are concerned about their health and who aren't concerned about their health. There'll be an equal representation of all of those factors in the groups because we've done some random sampling. Now we ask, which of these groups actually went and got screened? And let's say we find out that in the experimental group, the ones who saw the ads, it was 35%, and in the control group, it was 30%. This experiment now more accurately reflects the impact of showing ads to people. Is this making sense? Now, is the 35 significant enough to draw a conclusion about the efficacy of the ads? To answer that question, you have to do some more learning about statistical significance and the way we conduct research. But this concept of experimentation being a much stronger proof for causality than observation is really, really key to lots of the research that we do. In practice, we actually like to do lots of research. So we repeated randomized controlled trials. And once we get a lot of research together, then we really draw strong conclusions. So the key idea is that experimentation is king. And we need to use experimentation to draw causality. Now, sometimes you won't have a choice, right? Like, let's say you're trying to research the impacts of war on people, or some real hardship someone's gone through. You can't set up a control and experiment group there because you're not going to go and, all right, put these people through a war and these people not. Yeah, you're going to have to use observational data, and you'll try and use some techniques to account for confounding variables and to get the best scientific response that you can. But the gold standard is experimentation, and in general maths, we say that we can only draw causality from experimentation.